So here we go with Unit 5D, Magnetism. Lesson A is Magnetic Fields and Forces. In this lesson, we're going to introduce magnetic fields and begin to look at the forces on charged particles within those fields. Once we know how to find those forces, we're going to look at how those forces cause those particles to behave. From there, in further lessons, we'll be able to look at how those forces cause charged particles to behave when those charged particles are within conductors, which will lead us to an understanding that electricity and magnetism are really just two aspects of a single electromagnetic force. But to begin, we're going to introduce the basics of magnetic fields and look at how we calculate charges on single particles within those fields. So here we go. Now we all have some familiarity with magnets to begin with. Back in grade school, you probably did some sort of experiment where you tested what materials would be attracted to a magnet. I can remember as a kid being amazed by being able to take little tiny magnets and push them around on a table with the repelling magnetic forces. It turns out magnets are really important to our world today. Everything from electric motors to TVs, computers, electric generators, trains, CD players, all depend on magnetism. It's a basic important circumstance then that magnetism and electricity are very closely connected. They're really two sides of a single coin that we call electromagnetism. Magnetism has a lot of similarities to electricity. Electricity involves two charges, right? A positive and a negative charge. Magnets have two poles, a north pole and a south pole. The fundamental rule for magnets is like poles repel, unlike poles attract. Just like charges repel, like poles will repel. Unlike charges will attract, unlike poles will attract. So I can take a north pole to a south pole of a magnet, they'll attract. South pole to south pole, they'll repel. So all magnets have these two poles. If I took this magnet and tried to cut it in half, okay, the two new smaller magnets will each have two poles. If I cut those halves into two more pieces, each of those two new magnets will also have two poles, and so on. We can never get a magnet in half and have only one pole. We've never been able to do that. If we would, it would be called a monopole, right? But we can't do that. So all magnets are dipoles. Now we all know that magnets can exert forces on other magnets, and we also know that they can interact with other materials. These other materials are called ferromagnetic materials. Things like iron, cobalt, nickel are all ferromagnetic materials. Things that are made with those materials then are not only attracted to magnets, they can be magnetized and turned into magnets themselves. Other materials, other things like water, glass, copper, graphite, salt, they are weakly repelled by magnets. We call those diamagnetic materials. Then there's also paramagnetic materials that are weakly attracted to magnets. Things like aluminum, oxygen, sodium, platinum, and uranium are all paramagnetic materials. But regardless of what the material is, all magnets set up a field around it that we call a magnetic field. So let's take a look at magnetic fields. So just like electric charges are surrounded by an electric field, magnets are surrounded by a magnetic field. We even can draw lines of force around a magnet to show the direction of that field and its strength. These lines are called magnetic lines of force, or we often will refer to them as magnetic lines of flux. Some of the characteristics of a magnetic field are that the lines of flux travel through a magnet. So they travel out the North Pole, they travel through the air in a curve, and enter in the South Pole, and then go back through the magnet. So what this means is the direction of the magnetic field is always going to point from north to south. The arrows point away from the North Pole, they point toward the South Pole. Where those lines are closer together, that field is strongest. And a line that's tangent to any point on a line of flux shows the direction of the field, which is the direction of the force that would be exerted on a north pole of a magnet. For example, in this picture here, 3 points are located on the lines of flux, and the corresponding forces that would be exerted at each of those points are shown. The force is always tangent to the line of flux, and the direction of the field is shown by these arrows here, going from north to south. Now, we can even see these magnetic fields when we put magnets in an area where we've got a lot of little tiny iron filings, they're called. They're basically little slivers of iron, and because iron is magnetic, they line up around the magnetic field of a magnet. So a single bar magnet, close up, the magnetic field looks like this. We can see those filings line up in the direction of that magnetic field. So they're pointing around from north to south. If we put 2 bar magnets with unlike poles facing each other, then we can see that there's a higher concentration of those filings between them because there's an attraction between them. So the magnetic field of the one magnet comes out and around to its south pole this direction. Okay, the other magnet goes from its north pole out here to its south pole here, and there's attraction between, and we can visualize what that field then looks like. If we place like poles together, so here we've got 2 north poles together, we can see an absence of iron filings between them, showing us that that field is empty there. Okay, there's no field directly between 2 like poles of the magnet. It's these properties then of magnetic fields that allow us to be able to use magnets for a variety of purposes. Your basic flat magnets, often called refrigerator magnets, have an arrangement of long U-shaped poles, and this arrangement forces most of the field to exit kind of that brown side of that magnet, and we can stick them onto refrigerators and filing cabinets and whatnot. A hard disk drive consists of rapidly rotating disks with a thin magnetic coating on the surface. Information for computers then is stored in little digital zeros and ones, and on the disk these are stored as little tiny magnetic dipoles. Each dipole is like less than 100 nanometers long, and their directions can be changed by the right head, a tiny little switchable magnet that skims across the surface of the disk. And the information can then be retrieved by the read head, a small probe that is sensitive to the magnetic fields of the tiny dipoles. We can even think of Earth as having like a giant bar magnet stuck into the middle of it with its Earth's then magnetic field surrounding the Earth. And we're going to take a look at more of that in class. For now, we want to move into looking at magnetic forces. Now, the symbol that we use for magnetic field is a capital B, and the most common unit for magnetic field is a Tesla. There are other units that can be used, such as the Gauss or the Weber, but we use in physics the Tesla. Now, like electrostatic forces, magnetic forces can be both attractive or repulsive, but the main difference between electrostatic forces and magnetic forces is that while electrostatic charge could be a point charge, magnets must always have a north and south pole. They have to be a dipole. Then we start talking about magnetic forces. We start by talking about magnetic forces on charged particles, because that lays the groundwork for us to be able to talk about magnetic forces in current carrying wires later on. What we have to keep in mind is that only moving charges experience magnetic forces. You could put a stationary charge in a magnetic field and it's not going to experience any force. Only a moving charge will experience force in a magnetic field. The force that is exerted on that charge by that magnetic field will be perpendicular to the motion of the charge and also perpendicular to the direction of the field. So the result of the force is to cause a deflection of that charged particle. It gets pushed to the side. The equation then for the force exerted on a moving charge by a magnetic field is this FB equals QV B sine theta, where FB is the force, Q is the charge of the particle moving in that magnetic field, V is the velocity of that charge, B is the magnitude of that magnetic field, and the angle is the angle between the velocity direction and the direction of the magnetic field. From this equation then, it's easy to see that the magnetic force on a charged particle is going to be greatest when the velocity is then perpendicular to the magnetic field. It's going to be 0 when the velocity is in the same direction as the magnetic field. So while the velocity and magnetic field direction don't always have to be perpendicular, the magnetic force and velocity of the particle are always perpendicular to each other. So we're going to get maximum magnetic force whenever both the force, velocity of the particle, and direction of the field are mutually perpendicular to each other. So we've got three different things being perpendicular to each other. It's easy to see then that we're talking about three dimensions here. To quickly figure out the direction of the force acting on a charged particle moving in a magnetic field, we can use what's called the right-hand rule. Now there are a couple of different ways to do a right-hand rule for magnetic forces on a moving charged particle. And if you're doing any kind of studying online or anything, you might see a couple of those different ways. But what I'm going to show you is it uses your thumb, your index finger, and your tall man. So using your right hand, you spread your fingers so that the index finger and thumb are perpendicular. Then rotate your hand to point the thumb in the direction of the velocity of the charged particle, and your index finger in the direction of the magnetic field. Then your middle finger then points so that it's perpendicular to both those fingers, perpendicular to your palm, and this will be the direction of the magnetic force. So we use your thumb as the velocity of the charged particle, the index finger as the direction of the magnetic field, and a tall man points in the direction of the magnetic force acting on that charged particle. One of the things I tell students to help you remember this is actually get out a pen, right, and write a V and a B and an F on those three fingers of your right hand. So let's take a look at how this works. Suppose we have an electron moving to the right in a magnetic field that points upward toward the top of the page or top of the screen. What is the direction of the magnetic force? Using the right-hand rule then, we're going to take this hand here and we're going to point the thumb in the direction of the velocity, which would be to the right. Then we're going to take the index finger and point it in the direction of the magnetic field, which is going to be straight up. The tall man finger is going to then point perpendicular to both of those. The only way to do that is to point it so that it would point straight up out of the page. So you can imagine this hand pointing so that the finger, the middle finger, is pointed straight up out of the page in this situation. Now that would be great, and that would be exactly the direction of the force acting on that charged particle if this charged particle were a proton. But it's an electron. The thing is, when the charged particle we're dealing with is an electron, the force will be pointing in the opposite direction of the right-hand rule. So while the right-hand rule in this case tells us that the force would be pointing up out of the page straight toward us, because it's an electron, it's pointing to the back of the page, going away from us. Now this poses a slight difficulty for us in that we are working with 3 dimensions, vectors working in 3 dimensions on 2-dimensional paper. So how do we show when something is going into the page or out of the page? Well, if we want to depict a magnetic field that is perpendicular to the sheet of paper that we've drawn the thing on, we can do this in 2 ways. If the direction of the magnetic field is out of the paper, then we represent the lines of force as little dots, like this. To show a uniform magnetic field that is going into the page, we show little x's. You got to think kind of like an arrow, right? These are vectors, so we're dealing with vector arrows. If you've got an arrow pointing straight at you, you're just going to see a little dot coming at you. If you've got an arrow going away from you, you got the feathers in the back of the thing, you're going to see a little X going away from you. So this, little dots or little X's, will work whether we're talking about a magnetic field that's coming up out of the page, or if we're talking about a force on a particle that's coming out of the page. We draw a single dot with a circle around it usually to show the force coming out of the page, or an X with a circle around it to show the force going into the page. In either case, you're going to see several examples of these as we work on problems in class. We'll see you then.